In this section, we're going to take what we did with implicit differentiation and basically attach story problems to it. So these kinds of problems are called related rates. And it's really not anything frightening. The story problem aspect of it can get challenging for the usual reasons that story problems are. But basically, the first point that we need to consider is that in these problems, all functions, or excuse me, all variables are functions of t. Functions of t. And we're going to use t for time. So, for example, we're going to look at, let's just take a really simple equation here, y equals x plus 1. So this equation relates two variables, two functions together. We're going to think of y as being a function of t and x as being a function of t, and they're related together in this way. Now, what we're going to do with this is then, if the functions are related this way, then we know that the derivatives have to be related in some way. And when we say the derivative here, we mean always with respect to t. So because everything is a function of t. Okay, so if this is our function, then when we take the derivative of both sides, we're taking the derivative with respect to t as the variable. And so that's going to change, oops, that should be of 1, sorry. That's going to change how we actually take the derivative. So some of this is going to feel pretty natural based on the last section. What's the derivative with respect to t of y? Well, it's dy dt. Now that's kind of similar to how we had dy dx before, but now t is the variable, not x, or the independent variable. Now, similarly, just like before, the derivative of a constant is 0, so I'm not even going to write it down. Well, actually, I'll put plus 0 just to be picky. But what about the derivative of x? Now, previously in the implicit differentiation stuff, we were doing the derivative with respect to x of x. So this t down here was an x, and hence we got 1. But now we're differentiating x with respect to t, and remember, all variables are functions of t. So what's the derivative of x? It's dx dt. And so from this relationship of the two variables, we have this new relationship between their derivatives. Okay, so let's look at maybe a little bit more exotic of a problem. Okay, so in this first one, we're given that y is the square root of x, and we're asked to find dy dt when x is 4 and dy dt is equal to, or excuse me, dx dt, sorry, let's back this up here, dx dt is equal to 8. Okay, now, so this is a little different than what we had before because now we've got some numbers here. So the first moral here is ignore the numbers for now. We'll need to plug these numbers in, but don't plug them in initially. So here they tell us that we are interested in something when x is 4. I'm not going to go ahead and plug in x equals 4 now. I'll do that in a minute. Okay, so I'm going to take the derivative of everything over here, just like we did over there. So I know that dy dt is d dt of x to the 1/2. Why 1/2? Because it's square root. And now what is the derivative of x to the 1/2? It's 1/2 x to the minus 1/2. But then by the chain rule, we have to take the derivative of x, and as we said, that's dx dt. So we get a relationship here that dy dt is 1 over 2 square root of x, that's this part right there, times dx dt. So the derivatives are related together. Now, this is a little different than the last example because of this term right here. Still has an x in it, and that's okay. That usually happens. Okay, so now that we've taken the derivative, now plug in. We're trying to solve for dy dt at a particular time. So I'm going to write this with a little vertical bar here to mean that I'm plugging in x equals 4. Yeah, let's clean that up a little bit here. X equals 4 and dx dt is 8. So if I do that, and if I plug those numbers into this expression here, then I'm going to have 1 over 2 square root of 4 times dx dt is 8. And then if we just compute this arithmetic, square root of 4 is 2, 2 times 2 is 4, 8 over 4 is 2. So that's our answer. Okay, so let's just kind of recap what we did. First step was to take the derivative of everything. And this part kind of feels like what we did in the implicit differentiation section, with one important exception. Now everything depends on t. So you're going to have a lot of dx dt, dy dt's, d whatever dt's. And then after we've taken the derivative, then is when we start plugging in the specific numbers. Now the reason that we've got to do that is if we went ahead and plugged in x equals 4 here, we would get that y equals 2. If we take the derivative of that, we get 0 because the derivative constant is 0, and that's not particularly interesting. It doesn't tell us a relationship between the derivatives, it just tells us a particular value that happens at a particular point in time. This expression gives us the relationship for all time between the two derivatives, and in this case it also depends on x, which is interesting. Okay, so this is the kind of thing that we're going to talk about in class, but we're going to attach stories to it. So let me just kind of give you a quick rundown of the kind of story that we're going to ask. So I'm going to draw a quick picture here, just real free form. So let's say that I've got a building here, and I want to put a ladder up against the building. So here's going to be my really ghetto-tastic ladder. And let's say that the ladder starts sliding down the wall. Now you can imagine that the rate at which the top is dropping isn't always the same. It may speed up and it could potentially slow down, although here it probably speeds up. So the rate at which the top of the ladder is falling is not constant. And similarly, the rate at which the bottom of the ladder is moving to the right might also not be constant. So the relationship between these rates might be not an obvious function, not an obvious relationship, and so what we'll end up with are expressions just like this one here, that the rates are related by some equation, and there might be terms in here that depend on x, so that this relationship is not a constant relationship. It varies over time, and that's what happens here with the ladder. So another good example of it would be, and I'm sure you guys are going to like this one, so let me draw a martini glass, and let's put some, well, we'll make it red here, and we'll say it's a Cosmo. Okay, so if you've got a Cosmo and you start drinking it, what happens to the height of the liquid in the beverage? Well, when you first start sipping it, the rate at which the height is dropping is pretty slow. But as you make it to the bottom, the height at which you're drinking goes pretty fast. And now you're all familiar with this from having drinks, hopefully not Cosmos. And you know, restaurateurs can sort of exploit this fact, right? Because it looks really big when you start because you're presented with this gigantic circle, but there's this cone underneath here. that's only 1/3 the volume of a cylinder, and so it looks bigger than it actually is. Um, and so the idea that the rate changes as you get further and further into the drink, even if you say drink it at a constant volume per time, the height of it, the amount of fluid remaining, that or the amount of fluid that looks like it's remaining, that changes based on how much you've consumed. So again, there might be a relationship between the derivatives, the rates all of everything involved, that's not a linear or not even constant relationship. And this related rate stuff will allow us to describe those relationships and then hopefully solve sort of interesting problems.